are in listen-only mode.
Hello everyone, this is Terry Ersman. I'm the Chief Marketing Officer for Percona. Welcome to today's webinar. Before we get started, could you please raise your hand in the GoToWebinar window if you can hear me? Let's make sure good sound. Great, I see lots of hands raised. Thanks everyone, appreciate that. We will be making a recording of today's webinar, and we'll send a link to everyone who registered within 24 hours along with a link to a copy of the slides that are presented today. If you have any questions during the webinar, please enter them in the questions panel in your GoToWebinar control screen, and we'll answer as many of those as we can at the end. And if we don't get to some, we'll try and answer those later in a blog post. So with that, I would like to welcome Bill Karwin. Bill is the principal instructor in our Percona training group, and today's webinar will be on read-write splitting for MySQL and PHP. Bill?
Thanks very much, Terry. Good morning, everyone, or afternoon, wherever you are. My name is Bill Karwin. I'm going to be talking about read-write splitting for MySQL and PHP. This is a really interesting subject. It's about scalability. The goal that we have is to be able to handle a large amount of query traffic to our websites or applications in PHP and be able to continue to scale out as the level of traffic increases. A single database server can only handle a finite number of finite quantity of traffic. If we measure this by queries per second, you can only scale up so far. There's ways that you can increase the capacity of your server, but eventually your traffic will continue to increase exponentially until it can't be served by a single box anymore. So one of the strategies is add more database servers to handle more of the load. If we can design PHP applications to query one of a multiple of servers that have identical data, then we can increase the capacity of queries per second by spreading that load, and hopefully do it in a way that is transparent to the application. Replication in MySQL, built-in feature, is very useful for this type of scenario. If you can write changes to a master database instance, MySQL running on a single server, it can then share those changes among any number of slaves in your cluster. Eventually those changes will propagate to slaves, and I'll just mention why that is true in a moment. But the idea is that all of these database servers would stay as close as possible to having identical data. So then, although you've written write queries, those update, insert, and delete queries to the master, the application can then send read queries, select, show, those types of queries, to any one of the slaves, and it should give usable results. By this manner, we can spread the query load over a variety of servers that give you greater capacity for your handling your web traffic. Why I said eventually is that there's a difficulty with MySQL slave lag. Because replication is asynchronous, that is, when you make a change on the master, it returns immediately and doesn't wait for all the slaves to gain the same change. There's always the possibility that if you were to have your application query a slave too quickly, it wouldn't see the change that you just made on the master. It may take milliseconds, or it may take whole seconds, or even longer for that change to propagate to the slaves. This is unavoidable because when you make changes on the replication master, those changes aren't actually written into the log until you commit the transaction. So if you were to do a complex change or a long-running change, it would maybe take some time before it gets written into the binary log on the master. Then the binary log is downloaded incrementally to the slaves, and they each do this asynchronously. And then once it's downloaded, the slave executes the changes as rapidly as it can. But it has a risk that, so there's already a built-in risk that there's slave lag because the changes could take multiple seconds on the master to complete, and therefore they would take multiple seconds on the slave to complete the same thing. But there's also the case that they queue up. The replication slave can only execute one change at a time in its SQL thread. It's doing so serially rather than in parallel. On the master, many changes can be going on at the same time. So any change that takes multiple seconds will cause the others to queue up on the slave, and therefore changes, even though they are individually quick, they could be behind one that is long running. MySQL also supports semi-synchronous replication. There's a mode in which a slave can insist that the master wait until the slave has received the change before the master counts the change as having succeeded. That is, when you commit on the master, it writes it to the binary log, then waits for a semi-synchronous slave to download that change in that binary log and save it to its disk. But this is only semi-synchronous. It doesn't wait for the slave to execute the change. So there's still the possibility that the change itself takes multiple seconds and therefore causes the slave to lag behind the master. It won't have applied the change at the same time as the master reports back to the application that it has succeeded. So we have to face this. Slave lag happens. Even when using semi-synchronous replication, it is normal and expected that the slaves are not always perfectly in sync with the master. They will be within a very brief amount of time, and we can try to make sure that that happens as quickly as possible. Techniques to try to ensure that to keep up to date would be to make sure that the slave has hardware that is fast enough to execute those changes serially as quickly as they ran in parallel on the master, or to make sure that changes are simple and not long-running. If you need to make a complex change, it may be worthwhile to break it up into smaller changes. Or we can use row-based replication if the calculation of the change itself is what was taking so long. If it's a complex expression that is difficult to compute, then row-based replication can help to speed that up because it's copying the results of the change rather than the statement. I'm not going to go into a whole lot of detail in this talk about how replication works or how to set it up. There are other resources for that. For example, the manual itself and some good books that we can recommend. And also there's a recent blog post on MySQLPerformanceBlog.com written by my colleague Aramas about how replication actually works. I'll provide a link to that as well in a follow-up. What I'd like to focus on, though, is from an application developer's point of view that we have degrees of tolerance about how much slave lag any given query can cope with. And this is important to us as application architects and developers. Let me explain what I mean by these degrees of tolerance. The question comes up, does the application always need the slave's data to be perfectly in sync or absolutely current? We could say yes, we of course want the slave to be always up to date, but there are certainly cases where it's less important to have that be the case. For example, if we're querying data which doesn't change very often, we could tolerate more slave lag. But there's also cases where we have changes that are going on rapidly, and we want to make sure that the slave has the latest changes before we can deem it safe to query from the application. So then we say no. We say yes and both no that the slave must or must not be up to date. It is actually more complex than that. The cases when we need the slave to be in sync are on a case-by-case basis. And even a single application may have a mix of cases where some queries demand that the slave be always up to date, and other queries are more tolerant of slave lag. I've tried to come up with some kind of nomenclature or categorization for the different types of or degrees of tolerance that any given query can have. strict, time, event, and lax. And these are just labels that I've given them. Let me explain what I mean by these. In strict tolerance, every query must always query from the master because there's absolutely no tolerance for any slave lag. There's a good example is when your application is reading and writing data in the same transaction or even in the same statement. Because the change doesn't actually make it to the binary log until you commit the change, if you need to read any changes that you have just done within the same PHP request that haven't been committed yet, those would be accessible to the same transaction that you're making the change in, but they would not be viewable by the slave yet, because remember I mentioned that the changes aren't actually recorded in the binary log until you commit, and therefore they wouldn't be downloadable to the slave until after then anyway. The example of insert into some table based on select is where you would be reading data and inserting it in the same statement. So it's actually, in a way, reversing the order. You'd be reading data and inserting it in the same query. There could also be any other situations where the data must be absolutely current and you can't account for any slave lag at all. If you have a site which is doing real-time transactions across many different sessions, for example, bids in an auction occur very rapidly, and there would be no tolerance for accepting any slave lag in that case, because when you get down to the wire on an auction, you can't have anybody say, well, I thought that the bid was $10, but it actually rose to $12, and I didn't see that because my session was querying from a slave which hadn't seen the latest bid. So there are certainly cases where you have strict tolerance against slave lag. Time-based tolerance is what I call it, when the slave must have recent changes, but a little bit of lag is okay. For example, a fixed number of seconds. This is okay if I query data that is 3 seconds old. For example, chat room messages might be tolerant in this way. If it's okay to read from the slave if it's 3 seconds behind, because you would expect people to be viewing this and it would take them 3 seconds merely to read the comments in a chat room. But if they need to see the most up-to-date comments, they just need to wait a few more moments, and then the slave will catch up and they'll be able to see it then. You might want to declare exactly what the tolerance is and have it be variable and choosable from the application developer's point of view. So you can choose, is 3 seconds okay, is 5 seconds okay, is 10 seconds okay, and be able to change that in a convenient manner. If the slave is lagging further than that number of seconds, then automatically have the query go back to the master, so it's guaranteed to be reading the most current changes. In viewing this pictorially, we can see that the master may be writing to its binary log and it's gotten up to position number 3000, hypothetically, in the binary log, whereas the slave is lagging behind some number of seconds. It's only executed up to position 2000, and there's some gap where there's further changes on the master that haven't been applied by the slave yet. The slave can report exactly how far behind it is. A statement that you can run either in the MySQL command line client, as I'm showing here, or in any programmatic interface. You can actually execute this as a statement, just like you would select, insert, update, or delete. Show slave status gives you a number of columns of information about the state of the slave. You would run this statement against the slave. One of the columns that it gives you is the seconds behind master column. It gives you an integer, number of seconds. What it tells you is the difference between the timestamp of the latest change it has executed in the SQL replication thread versus the timestamp of the latest change it's downloaded. It doesn't know if there's more statements yet to be downloaded on the master, but it does know what it has downloaded, and each change in the binary log has a timestamp. So it can easily do a difference between those two timestamps and tell you how many seconds behind master it is. How much impact does this have on the slave server to query this? Very little. It's actually doing this just getting information out of in-memory data structures, so it doesn't have to read anything out of the log in order to tell what position it's currently up to. I did some timings on this on my virtual machine to show a few samples. I ran this statement 6 times using the MySQL profiler to measure the duration of how long it takes to execute this. And it's only about 2 to 4 ten-thousandths of a second. And that's probably the maximum you can expect it to be. This is just running on a Linux VM on my MacBook Pro. So you would probably expect to see that be even quicker on a real production server. Event-based tolerance is the next level of tolerance of lag that I have. And this is a little bit more subtle. I don't really care how many seconds the slave is lagging behind, as long as it includes a particular change that occurred on the master that I'm interested in. And the scenario could be, for example, I am using an e-commerce site, I insert a line item to my shopping cart, and then my next action is to view the contents of the shopping cart. So I need to cause the application to do a select and view that content. As long as the slave has executed up to the point of inserting that line item into the shopping cart, it may nevertheless be lagging behind multiple seconds behind the master in other changes that are going on, because other users are using the site and they may be incurring long-running updates or high volume of updates that are irrelevant to the specific one that I'm looking for. In my session, I just need to see my shopping cart, and it occurred 5 seconds ago after I added that item add the item to the shopping cart, and the slave is easily caught up to that point. Visually, let's take a look at that. I could have a master binary log where my insert to my shopping cart occurred at position 1, 2, 3, 4, as shown on this diagram. The change was committed there. The master has continued to write more changes, and it's now up to log position 3000. On the slave, it has progressed to read the changes from the master. It has already passed position 1, 2, 3, 4. They're not lined up immediately right over each other because the slave took a few moments to account for that change. The slave is continuing to take changes from the master, and it is lagging 5+ seconds behind. It's only executed up to log position 2000. This is just hypothetical measures. There's no actual connection between the thousands and the 5 seconds. The case here shows that the slave is lagging behind at least 5 seconds, but it's okay because as long as it's accounted for the change that my session needs to see, it's safe to read that content from the slave database. Trying to find out if the slave has the right change means we need to know what the binary log position was when we made the change. So if the application is inserting an entry to its shopping cart, for example, it could then run a command show master status, and that will show it fields that show the binary log file that it's currently on and the position that it's currently on when that change occurred. The PHP application can save these two pieces of information in the session array so that on a subsequent request, the PHP application has access to that coordinate in the binary log stream and can then find out if it's up to date. Show master status is also very low impact. I measured that this takes about 1/10,000th of a second. It's, again, getting information out of statistics that are in memory, and it doesn't need to access anything more costly than that. So it's very safe for the PHP application to run this query and not have to worry about the impact or load. It can make in-memory operations very quickly without having to incur a lot of overhead to the I/O or the disk or so on. I was also looking in the source code to make sure that these statements show master status and show slave status don't incur mutexes. Those could be ways that it would form a bottleneck, so that if you had a high load of multiple queries against the same statement, they would have to serialize against each other. But it appears upon my reading of the code that that is not the case, that these statements are reentrant and can be executed freely by multiple threads. So I don't think that that's a big issue either. On the subsequent PHP request, when it tries to check to see if that change is in its version of the database that has already applied it, show slave status will show you the master log file and the execution master log position. That is, relative to the master's log file, how many changes has the slave applied. And those pieces of information are available in the show slave status. The task of the application then is to compare those values to the values that were saved in the session previously. And by comparing them, they can see if the slave is caught up to the position that has the change that it's interested in. Again, as we saw before, show slave status is very low impact. You can run this pretty freely on a slave without worrying about putting too much load on it. The final degree of tolerance is lax tolerance. That is, we don't care if the slave is lagging behind as long as it's not so far that would be causing problems in some other way that we would have to respond to. For example, if the slave is completely offline, we would be notified in some other way. But as long as the slave is still running and and has good health, we don't really need to measure how far it's lagging behind, because the query we're running is very tolerant of that. Examples: if we are reading data that doesn't change except very seldom, a lookup table. For example, maybe you have a list of postal codes or U.S. states or countries of the world. The likelihood that that data is going to change from moment to moment is very low. So it's very safe to have an application read that kind of data from a slave without even checking to see if the slave is lagging. Or in a scenario where it's okay to read old data, even data that's old by many seconds. For example, if you are displaying the count of likes or upvotes for something, what is the impact of showing an outdated version of that data? You could, if say you were YouTube and you wanted to show how many likes a particular video had, you could show that this music video had 16 million likes. What's the downside of having that be a few seconds out of date? Very little. The next time somebody refreshes that page, they'll see the updated view, provided that the slave has caught up a little bit more. But the impact of that is not very time sensitive. Which method is the best to use for a given application? All of them, because any given application is going to have a variety of different use cases, a variety of all the different types of queries that have different levels of tolerance to the slave lag. An e-commerce application may have an event-based tolerance for viewing the contents of a shopping cart, but it may have a much lower, more relaxed degree of tolerance for showing the products in the product catalog. That could be minutes out of date if necessary, because the items in the product catalog don't change very often, and hiding a brand new product for 60 seconds while the slave catches up is not so much of a big deal. What we'd really like to have is some sort of productivity tool that allows us as PHP developers to choose these different levels of tolerance very easily and on a case-by-case basis, so that we don't have to engage in all the detail work of querying show master status and show slave status and keeping track of all that in a very detailed way. That would be a lot of work that we should be able to delegate to some sort of database access library. So, with that in mind, I've been working on a proof of concept of such a database access library to try to make sure that we have something that can allow us to be productive and yet also take advantage of all the range of these degrees of tolerance and architect our applications to match that. What are the requirements for this database access library? Well, I want to have a way to transparently map my SQL queries to either the master or multiple slave instances. So the connection object in my application needs to know about all the instances of MySQL, both the master and the slaves. The API has to send read queries to a slave on demand. It could load balance across multiple slaves randomly, that is, choose one at random to delegate read queries to, or do so round robin or some other method. Also detect if the slave is lagging too much based on the degree of tolerance that we have declared for that particular query. And if it's not usable, if the slave is lagging too much, then the database access library should automatically switch that query back to another slave that is caught up enough. Or if none of the slaves are caught up enough, then automatically switch back to the master to query that. And also detect an offline slave. If a slave is not running at all or cannot be connected to, then it should choose a different slave, or if none of the slaves are running, then switch back to the master again. What I found was the Doctrine project, a popular database access library and object relational mapping tool for PHP 5, has a part of the solution already implemented. They have a class MasterSlaveConnection. It extends their standard connection class, and it constitutes an example of a custom wrapper class. The architecture of Doctrine allows a connection to use a custom class, and you can declare that in your connection parameters, which class to instantiate to handle the connection. And the only such wrapper class that they have implemented and included in their DBAL library is the MasterSlaveConnection. Their implementation of MasterSlaveConnection satisfies some of the requirements that I had on the previous slide. That is, it tracks multiple instances, a master and several slaves. It chooses randomly between them and fails over back to other slaves or to the master. But it does not detect the lag level of the slave, and it also does not detect if the slave has gone offline. So I started extending this wrapper class. Starting with their MasterSlaveConnection class, I created my own new base class. I called it Base MasterSlaveConnection, which implements some of the logic that I wanted to try to test if the slave is usable, to allow you to specify which one you have. And then for each of the different levels of lag tolerance, I had a specific subclass: strict MasterSlaveConnection, time MasterSlaveConnection, event MasterSlaveConnection, lax MasterSlaveConnection. And you would, when you connect to a Doctrine connection in your application, you have to pick which one you want. And you could change maybe multiple times within the scope of one PHP request. To declare these, I just collect all the class names into a hash array just to list the wrapper classes, and then at any time I can choose the class name of the type of connection I want by looking up a mode or a tolerance level in that hash map. So I just choose the wrapper classes sub mode, and that becomes the class name that I want to use. And then when passing connection parameters to the means by which I connect to the database, I have to declare the wrapper class that corresponds to the mode that I want to use for this particular request. Here's some examples. I have a master, which is host Huey, and it has a user and password, and then some number of slaves. It could be 2 or 3 or any number that you want. I have slaves Dewey, Louie, and Daisy. Then it's all a matter of calling the doctrine function for getConnection and passing the connection args, and part of the connection args declares which subclass, which wrapper class I want to use. If I have time or event, I may also need to set the number of seconds of lag tolerance or the target binary log coordinates that I want to listen to. And those are only applicable for the subclasses corresponding to those tolerance levels. Then finally, connect. The MasterSlaveConnection wrapper class accepts an argument of either master or slave, the literal word. And when you choose master, it'll always connect to the master. If you choose slave, it will connect to one of the slaves that are in that pool. It will choose one at random, and then in my extended classes, it will test to see if that slave is usable based on the tolerance level of the mode you chose. The way that the MasterSlaveConnection wrapper class works is that read queries called with the execute query and execute cache query will obey the behavior of switching to a slave if necessary, if you've chosen the slave connection and the tolerance is satisfied. All the other methods of the connection will automatically map back to the master. So if you're doing any write queries or updates, deletes, inserts, any transactions, any commits or rollbacks, all of those methods are only going to use the master. So when the connection occurs, it's actually making a connection both to the slave and the master behind the scenes, and then using the slave if it can for a read query. Otherwise, it will just switch back to the master connection and execute them there. So demo time. I wanted to show you just a small sample of the code. Here's one of the functions in the wrapper class for the time-based. You can see that I have implemented a function called isSlaveUsable. It first tries to find out what the server ID is so that it can map that back into our array of instances, and then uses the showSlaveStatus command, runs that, makes sure that the slave SQL running field from that output is equal to yes. We wouldn't want to query a slave if replication has actually stopped. And then finally looks at the seconds behind master from that row and compares it to the target seconds behind master, which we would have had to set in our application. If target seconds behind master is 5, then we have to make sure that the current seconds behind master of that slave is less than that number. Otherwise, it would fall through. The state of that slave would be lagging. It would also, in my debug output, record the seconds behind master and return false. So that in that case, if it doesn't return true because it was within the range of tolerance, then it would fall through, return false, and isSlaveUsable would be to tell that this slave cannot be used. It would trigger the connection to try a different slave, round robining through the set of them, and then finally getting back to the master if none of the slaves satisfy it. Let's see that in action. I've set up this very simple PHP application that allows me to look at my array of the master, Huey, and 3 slaves, Dewey, Louie, and Daisy. As long as I'm using strict mode, then I can select from that master, and it will always be selecting from the master. The green box indicates that it's using the master. If I go to lax mode, it will choose one of the slaves at random. And as I'm clicking this multiple times, you can see that the random choice goes round and round between the slaves. It doesn't not do round robin, it just chooses one at random, so it may choose the same one multiple times. What about time-based? If I want to say the slave must be within 10 seconds of the master, and I execute an update against this, my update is customized to take 5 seconds. So there we go, it ran an update, and then as soon as I try to select, it decides that the lag is a great deal more than 10 seconds, so all these slaves were chosen and determined that it couldn't use them. The number of seconds shows up as very high number of seconds because it actually is measuring between the latest executed and the latest downloaded, which gives you some weird anomalies. Because I haven't run this demo in about an hour and a half, the delta is actually shows up as that number of seconds, at least for cases when you haven't done an update in an hour and a half. And then as the slaves catch up, it will go back to using them. And let me try that again. I'll do an update. It'll take 5 seconds. Now it's only been a few moments since the last time I did an update. So we see it's only been 60 seconds. And then finally, if I hit select a few times, then finally the slaves execute that 5-second update, and they get back into the case where they're usable. And I can continue doing that. In the event-based, I do an update. My application records the binary log position on the master to do the update. And then when I try to do a select, it determines that it's lagging behind. It's looking for a given binary log position, file, and byte offset, and it can't find that as being executed on the slave yet, so it actually says I can't use these slaves. It has actually tested all 3 of these slaves and determined that it's out of date. And then if I were to select again, it's been a few moments, so it's caught up, and now it's usable again. And finally, Lax, as we saw before, always allows me to do that if I do an update against the master, waiting, and there's done that, and even though it hasn't executed that change on the slave yet, I can still select from the slave. Okay, so what's next? Some of the caveats of doing this, even though there's objects that encapsulate these different degrees of tolerance and can allow you to do this, you still have to make decisions as a developer on a case-by-case basis whether a given query that you need to run is strict, time-based, event-based, or lax in its tolerance of slave lag. And you could have many such decisions within a single application or even within a single PHP request. Another caveat is that because this architecture in theory permits your traffic to be automatically switched over to the master, you have to make sure that the master can handle that much traffic in the event that that happens. What I mean by this is if you have a master and 3 slaves, as I showed, and you have a scale of traffic, a number of users and requests per second, which is it has to scale out over that number of machines, that number of database instances in order to support your scalability. And then suddenly at one moment of the day, a long-running update causes all 3 of those slaves to be unusable. Without any action from you, a large amount of your traffic could be pushed onto the master. Can the master handle that much traffic? It's essentially 4 times higher than its normal traffic that would be running on that master. And therefore, you need to have capacity planning such that, at least for brief amounts of time, the master can handle that much query traffic and not either crash, that is fall over and absolutely not be able to take any more traffic, and also not become so slow that it harms your website usability. And hopefully it'll happen briefly enough that your master database instance can handle that amount of load that for brief periods of time, and then as soon as the slaves have caught up, it will delegate back to them. I've seen a number of different attempts at doing this sort of load balancing and detection. In one case, the application framework would, for one particular website, would detect the seconds behind master on the slave And if it was over a certain degree of tolerance, it would remove that slave from the pool of slaves that could be chosen, and it would keep it out of the pool, ensuring that it wouldn't be chosen for up to 120 seconds. But the impact of that was they lost capacity of that slave for all types of queries for that 120 seconds. And I had to ask them, is that long enough for the slave to catch up? Is it too long? Perhaps the slave caught up in the first 3 seconds after that decision was made, and you're essentially not getting the use out of that slave for read capacity for 117 seconds after that. And there's also, you could reason that there is further queries that are more tolerant of slave lag that could be sent to that slave, so you're losing out on that as well. So there's, hopefully, by having a framework like this that allows the application to cheaply decide on a request-by-request basis and even a query-by-query basis whether the slave is usable for a given query, we'll actually, on average, make use of a slave more often than the scenario where we remove the slave from the pool for extended periods of time, hoping that it will catch up. There's another solution. The PHP native driver for MySQL has a architecture that supports plugins, and one of which is the MySQL ND MS plugin. MS is for master slave. This plugin allows any connection to be delegated across a set of master and slaves, and it occurs below the level of the database access library in PHP. This actually is managed by the MySQL ND driver itself. So the MySQL ND driver supports a configuration file with which you declare, like I declared my connection parameters for Doctrine, but you declare the master and all the slaves at that level. And whenever you run a select query, it chooses a slave with a variety of different methods, either round robin, random, or even a user-defined callback. So you can implement a function in PHP to choose which slave instance you want to use. The MySQL ND MS plugin is a separate install. You probably are running the MySQL ND driver on any modern version of PHP, but the MS plugin is a separate download from PECL. Unfortunately, as I went to try to test it out, I discovered that the current version of the MS plugin requires PHP 5.3.6 or greater, and that some features require 5.4. However, the current PHP package on Red Hat or CentOS repositories is still 5.3.3, and so when I tried to build the MS plugin, it wouldn't build. It was, it couldn't compile it, and it was referencing symbols that are not present in the older version of PHP. So I didn't get to test this out. I didn't want to install a more current version of PHP and risk changing my environment when it was so soon before I was going to run this demo. The other question that I need to experiment with for the MS plugin is if it's choosing the slave based on a user-defined callback but below the level of the application database access library, how can we specify a tolerance level to affect the way that it chooses the slave? And this may require us to code that user-defined callback function to choose an instance based on application global variables so that we can inject in some way some ability for the database access library to choose what level of tolerance and then have that actually affect the lower level library in the MySQL ND driver. Still not sure how that actually can communicate that to that lower level, but it's worth giving it a try. What I need to do further for this proof of concept is make the code available so that all of you can experiment with it and use it as a starting point for your own work or even contribute it back to the Doctrine project. I recognize that one of the caveats to that is that Doctrine is supposed to be a library which is usable by many brands of database, not just MySQL, although there's probably a lot of synergy between PHP developers and MySQL sites. That it's not 100%. We have to account for people using Postgres and SQLite and Microsoft and Oracle and all the rest. So putting in MySQL specific commands like show slave status and show master status kind of upsets that. We may need to be clear that the wrapper class has to be MySQL specific in order to function in this way. Another to-do is to, like I said, experiment with the MySQL ND MS plugin. And there's information about that in the MySQL manual. I give a link at that point. And then, of course, more testing, more performance testing, load testing to make sure that this continues to be low impact even at high load and high concurrency and high scale to make sure that the solution I've come up with is actually something that works out well. So that's what I've got. I wanted to remind you that I'm a principal instructor within Percona training. And we have a really great set of offerings of classes that we offer around the country in the US and Canada and in Europe. We can also do custom on-site training for MySQL. We cover a lot of database administration topics, database developer topics, and internals of InnoDB, and so on. You can see our schedule and offerings at percona.com/training at any time. And I'm also speaking coming up in the Santa Clara MySQL User Conference at Expo in April this year. You get a discount code for having stayed with me throughout this presentation, Percona 10. That's Percona 10. If you want to register for the upcoming MySQL conference at Expo in April, you can use this discount code when you register and get 10% off. So thanks so much for listening to me. I'd be glad to talk about questions. We could talk about anything replication balancing related, and if I can't get through all of them, I'll gladly post follow up in a blog post.
Okay, good. Thanks, Bill. Again, just to remind everyone, if you have a question, please submit it through the GoToWebinar control panel. You can put it in the question section there. First question we have is, does storing the position in session lead to local storage and limit scalability?
Good question. The session variable, as implemented in many sites, actually writes data into the database itself. So I find that actually is not necessary. What I choose to do on high-scale websites is actually write the session data to some faster repository like memcached, or if you're using PHP environment, you can use APC or some of the other caching layers that are built right into PHP, and that'll be much higher speed. It's good for session data which is ephemeral in nature. That is, if that were to go away, if for example, your volatile in-memory cache of the session data were to expire because memcached crashes or something, then the impact is somebody would have to log in again, and they would reset their session. But under normal circumstances, it's a big win because it's faster, and the data in there is ephemeral anyway. So yeah, the session data could impact the scalability if you are writing it to a durable repository like a database server, but that's usually not necessary.
Okay, next question. The question is, are there similar plugins or resources for Java-based applications?
I haven't come across any. I think there are frameworks that can do balancing over that. I've also noticed some for the Ruby language. I was investigating to see if there are any of these types of languages, packages for Ruby on Rails. There are for Ruby on Rails. I investigated that and found there are about a dozen, actually, 8 to 12 that I found. However, none of them do the automatic failover to the master if the slave is lagging behind, and none of them even has any detection of how much lag there is in the slave. That is, they may have the capability of splitting the read-write queries between a master and slaves, but it has no ability to tell whether the slave is quote-unquote safe to query from, and that was kind of disappointing. The other disappointment is that many of those projects don't have any tests or documentation, so I wouldn't necessarily advocate using them in production. They may be useful for proof of concept, but they didn't seem like they were mature enough to use in production. And I haven't really specifically looked for Java or other languages to see if there are similar packages. That would be an interesting research project to see how many of those out there. But I suspect that the same is true, that there may be some that do read-write splitting but don't do the checking to see how much the slave is lagging.
Okay, next question. Is RBR faster replicating versus SBR replication?
Good question. You're referring to row-based replication versus statement-based replication, for everybody who isn't familiar with those acronyms. It could be, as there are certainly cases where row-based replication can be faster because it's only replicating the results of the changes rather than the statements that will have to get re-executed on the slave. In statement-based, the slave would have to parse, optimize, and execute the same SQL expressions and queries, and that can be a lot more work than simply taking the results of the change verbatim from the binary log and applying them back into the database. So it's often the case, although not universally true, depends on the nature of the query, whether or not the row-based replication is faster, or by how much. On average, I would expect it to be a bit faster for a typical workload, but it really depends on your application and the types of queries that you're running.
Okay. Next question. Can you compare or contrast this approach with using a write-through cache?
Using a write-through cache, you could avoid replication altogether, and the changes that you are saving to the database would be saved in memory and then also applied to the database on subsequent reading. If the entry is still in the cache, you could just utilize that. In fact, in MySQL, when using InnoDB, it functions very similarly to a write-through cache because of the InnoDB buffer pool. Any changes to pages that you make involve copying the page into memory, modifying the page, saving the nature of the change to the InnoDB log, but then subsequently if you read the same rows, they would be coming right out of the InnoDB buffer. So it's effectively like a write-through cache. And that is, it's saving it durably, but also preserving that page for subsequent reads at high speed. And what we're really looking for is a means to scale up even further than what the write-through cache could provide. That is, the read-write splitting allows us to expand the read capacity over multiple servers, not just from memory.
Okay. Next question. Would it work with the ORM layer of doctrine, considering it would only work for one work of unit?
I haven't experimented with using this for the ORM layer of doctrine. What I was doing for this proof of concept is modifying the database access layer itself. Since the ORM uses the database access layer, it should be usable in this way. But the tricky part is that the ORM would need to choose the right subclass of wrapper class for the database access layer connection. And so you may need to instantiate multiple ORM objects, each with their own respective connection type based on the wrapper class subtype. And so it could get a little tricky to try to manage that within an application architecture to be able to dynamically choose that. What would be nice is to have a wrapper class which doesn't necessarily limit it to one type of tolerance, but actually can switch dynamically based on the application requirements, so that you could do that, inject that different type of behavior independently of the choice of the wrapper class. I was just implementing this as one class per tolerance level to keep the code a little cleaner.
Okay, next question. Would opening multiple database connections to the master and then subsequently potentially a number of unsafe slaves result in a high performance cost?
Well, the cost of opening those connections isn't so high as actually executing changes within those connections. The overhead of making a connection is not that bad. And as a footnote, in MySQL 5.6, I've seen some announcements that the speed of making a new connection is being improved even further. Even though MySQL was pretty low overhead to make connections relative to other brands of database, in MySQL 5.6 they're improving it even more. So that's some good news. And the other cases that if that is an overhead, there are means by which to use connection pooling or persistent connections to reduce that overhead. So the way that this would work is hopefully those connections to the master and the slaves would be reused, and the overhead would be very low. If you're actually executing changes against a given connection, it's just essentially idle.
Okay, next question. Can the solution you proposed be used with ExtraDB cluster, or are there any other issues we should look for?
There's no reason why it can't be used with ExtraDB cluster. The solution would allow you to specify a given instance as the master for this, and then other connections for the other slaves. In ExtraDB cluster, for those of you who haven't studied it yet, that architecture is where you have some number of instances that are always in sync with each other. So that is that they're always copying changes to all of the nodes in the cluster, as opposed to the asynchronous nature of traditional MySQL. So the impact for ExtraDB cluster is you can write to any of the nodes. You don't have to designate one as the writer or the master. They're all effectively masters as well as readers. What I would expect to see for an architecture for ExtraDB cluster, assuming that all these instances are in the same data center, is that you might have multiple application servers running PHP applications, and a subset of your application servers would treat machine A as its write master, whereas a different application server would treat machine B as its write master, and therefore balance the load that way. And yet any one of those instances could query any of the slaves in the cluster, whichever it keeps up. However, I'm not sure if ExtraDB cluster reports the master and slave binary log position in the same way. So this doctrine implementation that I've just come up with may not get the right information out of those instances by showing master status and slave status. That's a detail about ExtraDB cluster that we'd have to investigate further and test with this this implementation I have. This is really an implementation intended for use with traditional MySQL replication.
Okay, next question. For randomizing the slave requests, should we use some randomize function or HA proxy?
Well, the intention that I had with this implementation is that the randomize function is already built in. So just by virtue of having listed the slaves in the connection parameters for the doctrine master slave connection class, it already knows how to randomize between them. There's no need for you to do that in your application code. It handles it in the database access library. But if you wanted to do any kind of custom randomization, for example, if you had a better random function, or if you wanted to give higher weighting to a given slave than the others, or to be able to control dynamically which ones were part of the pool of those to be chosen, that would be further customization, and currently the code doesn't support that. But ideally, the intention is to make it as transparent as possible and allow the application programmer to get other work done instead of worrying about randomizing their slave choice.
Okay, very good. Well, unfortunately, we're out of time for today. There were some questions we didn't have a chance to address, so we'll pass those over to Bill, and he'll follow up with a blog post to delve into some more of your questions. Thanks for everyone for attending today. Please check out our webinars page regularly, as we are continually adding new webinars in the future, and we look forward to seeing you at a future webinar. Thank you, Bill.
Thank you, Terry.
Goodbye, everyone. Have a good day.